Hi there, folks. Welcome to our first lesson on electrochemistry. Okay. When we're talking about electrochemistry, we are talking about something known as redox reactions, right? And so what we're looking at here is we're looking at two different species. One will undergo reduction, the other one will undergo oxidation. Okay, so let's look at that first example on here that we have. And we've got this iron solid being dropped into this copper 2 plus aqueous solution. And from here we produce aqueous iron and we solidify out that copper. And we've done this in Chem 11 as a single substitution reaction where we dropped an iron nail into some copper 2 chloride solution, and we noticed that our solution went from the bluish green of the copper to an almost clear of this iron, and we start to form what looks like rust on that nail, but it was actually copper. Okay, and so what we have here is, although we've talked about this before as a single replacement reaction, it is also a redox reaction. And so what we have here is we have this iron, okay, and this iron is undergoing oxidation. Okay, and at the same time, our copper is undergoing reduction. Okay. And now in these notes, I've got a few different ways that we can think about what's happening in here, but essentially, an object that is being reduced, this copper going from a 2 plus to a copper 0, that charge is being reduced. It's gaining 2 electrons. Okay, so as it gains those electrons, its charge is reduced, hence being called the reduction. And likewise, we've got this iron undergoes oxidation as it loses those electrons to go from the solid iron to the aqueous, from a charge of 0 to a charge of 2 plus. Okay, and the reason why part of the reason we call this an oxidation is that if we have solid iron and it rusts, this is when it's being oxidized. Okay, and so part of that being oxidized is it is going from the 0 charge to a 2 plus charge so that it can bond with that oxygen. Not the only reason, but it's a good way to think about it and help you understand what's happening. Now, I've got a couple things on here that I've given to you as acronyms to help you understand. The one in the textbook is Leo the Lion says grr. So loss of electrons is oxidation. This iron is donating electrons to the copper, so it's losing those electrons, right? So losing electrons is oxidation. Gaining electrons is reduction. This copper is gaining those two and it's undergoing the reduction. Okay, and since electrons have that -1 charge, if they're gaining electrons, they are reducing the charge. Okay, the other one I gave you is oil rig, which simply stands for oxidation is loss of electrons, reduction is gaining of electrons. Okay, and that is the overall essence of what we're going to be talking about in this electrochemistry. We'll talk about some practical applications of it, and essentially it is this electrochemistry that allows us to have things like batteries and cell phones and all these other different types of things that require these batteries to be used. Okay. We also want to talk about this oxidation number. Okay, this is our second portion of this chapter. So our oxidation number, we've talked about before how we have these multivalent atoms, iron 2 plus, iron 3 plus, copper 1, copper 2. There's all sorts of these different elements out there that can have these multiple charges. Well, each one of those different states that we see, the 2 plus, the 3 plus, those are different oxidation numbers being applied to these different elements. Okay, and since elements can have different ones, we need to be able to understand how we can figure out what that oxidation number is of an atom or an ion, so that we can help to understand what is happening in our reactions. Okay, and we're going to start balancing those reactions later on, but we need to understand what's going on. Okay, I've listed out the rules for you. And for rule number 1, atoms in their elemental form have a oxidation number of 0. Okay, so I'm just going to write out the examples that we have here for you. Okay, so for number 1, we could have something like sodium metal or zinc metal. Okay, but we could also have elemental forms of things. So we can talk about O2, Cl2, P4, or S8. Okay, so any of these type of compounds or elements are going to be considered their elemental form, and they would all have oxidation numbers of 0. Okay, so just want to keep that in mind. We've got those 7 diatomics. I've listed 2 of them here, and then we also have phosphorus 4 and sulfur 8. Okay, just some new ones we want to keep into there. Okay, so all of these have oxidation numbers of 0. Okay, rule number 2. Monatomic ions, so single atom ions, whatever they're told their charge is, that is what we have. So for things like K plus 1, its oxidation number is 1. For Fe2 plus, that would equal 2. Fe3 plus equals 3. Okay? So these are all hopefully pretty straightforward. We can also have negative values for these oxidation numbers. So like in chlorine ion, this would be a -1. Okay, so we can just want to be careful when we're having these monatomic ions. We want to put those on there as well. 3, oxygen. Okay, so oxygen on its own as an ion is going to equal -2. If it's in the O2 form, it would have a 0. However, if it's oxygen bonded with anything, we're going to have it as a value of -2. So we can talk then about maybe Fe2O3. Each of these oxygens would have a charge of -2, or an oxidation number of -2. But we have exceptions. Okay, the first exception will be a peroxide. So we could talk about sodium peroxide, or our more common one, hydrogen peroxide. In each of these situations, oxygen has an oxidation number of -1. Okay, when it's on its own, like in a compound like this, it's a -2. If it's in the elemental form, it would be 0. If it's a peroxide, it's -1. And then that one other rare exception that we have is if it's an OF2. Okay, in this case, the oxygen has a +2 charge. Okay, and that just has to do with the electronegativity of fluorine. We'll talk about that one a little bit later on. Okay, so these are our first 3 rules. Elemental forms have a oxidation number of 0. Monatomic ions have the charge associated with that ion. Oxygen, outside of its elemental form, when we have it in a compound, it's almost always going to be a -2. Unless it's in a peroxide, then it's a -1. Or if it's in this oxygen difluoride, it would have a +2. Okay. Moving on to our 4th rule. Hydrogen is going to be a +1, except for when it's a metal hydride. So if we're thinking of HCl or H2SO4, okay, in these cases, hydrogen equals that +1. However, if we had, say, calcium hydride or lithium hydride, right, we're dealing with a couple metal hydrides here. In these cases, the hydrogen has an oxidation number of -1. Okay? When we are looking at compounds, the total value here sums to 0. Okay, so let's look at 2 different compounds, CuCl or CuCl2. In both these situations, we're always going to sum to 0, right? We've got 0 charge on these compounds, so our total charge has to sum to 0. Well, we are going to look at our chlorine is going to be -1, and our copper in this case equals +1. Whereas down here, our chlorine is still that -1. However, our copper oxidation number in this point is a +2. Right? Very similar to how we would balance out these ionic compounds and how to create these ionic compounds, but we just want to make sure that we understand that the total oxidation number in these compounds would sum to 0. Okay. I'm just going to clear space here for number 6. Our polyatomic ions. Okay. Polyatomic ions. They sum to the charge on that ion. So if we are looking at, say, ClO4 minus or ClO3 minus, okay, well, as I previously said, oxygen is a -2 outside of our exceptions. Okay, and so we need to find out what is our apparent charge on these chlorines. Well, I've got 4 oxygens, so 4 times -2 means I've got a -8 charge on my oxygens. Down here, I've got 3 oxygens at that -2, so that means I have a -6 charge or oxidation state for those 3 oxygens here. For this to sum to a -1, that must mean that I have a +7 for my chlorine here. And for this one, I'm also summing to a -1. If I had a -6, that must mean I have a +5 for my oxidation state of this chlorine. Okay. Number 7. This is more for when we are dealing with our covalently bonded compounds. Okay. Now we normally don't think of them as having a charge, but when we're talking about this redox reactions and I'm trying to understand which species are undergoing reduction and which species are undergoing oxidation, we still want to assign oxidation numbers, or these ionic charges, if you will, to these covalent compounds. So if we're looking at, say, a compound of PF5, okay, we're going to assign the negative value to the more electronegative element. Okay, this is part of the reason why that oxygen difluoride gives oxygen that +2, because when we're looking at this situation here, fluorine is the most electronegative element. Okay, so it would take on its most common charge, and so for fluorine, that is a -1. Okay, so since I'm dealing with a compound here that has no charge, I have to add up all of this to equal 0. I have 5 -1 compound or elements, so that must mean I have a -5 for my fluorine. That means I must have a +5 for my phosphorus. Okay, so we want to individually assign our oxidation states, oxidation numbers, following the orders in the rules that we have there. Okay, so hopefully that helps with these first few. My last example I want to talk about is in compounds that have more than 3, or have 3 or more elements. So let's consider SCN minus. Okay. So when we are looking at this situation, the way we write these out, and these are for those common ions that we are told, okay, not ones that we have to make up ourselves, but when we'll be told these for most of the place, or they'll be on our chart. Okay, we are going to assign the negative value to the elements that are the furthest right on our periodic table. So for this example, I'm going to start with my sulfur, then my nitrogen, and then carbon to finish this off. So sulfur, very similar to oxygen, would be a -2. Nitrogen would be a -3. That sums those two pieces to a -5. If our overall ion had a charge of -1, that means that our carbon ends up having that +4 charge. Okay. So these are those rules in identifying the oxidation states. I've assigned 4 questions on here. Number 3, although there are several parts to that one question, I do encourage you to do most of those to make sure that you really have a strong handle in identifying the oxidation states or the oxidation numbers for these elements. Because without being able to do that, this section will be very, very difficult to handle. Okay. Let's look at a couple examples that I have here of overall compounds and applying these rules to them.